Definite integrals of non-negative functions give areas of domains. Conversely, if areas of domains are known, then one can use that knowledge to compute certain integrals. In this set of solved problems, I discuss 3 problems related to the numerical evaluation of definite integrals. Let me start by recalling that definite integrals have been defined as limits of Riemann sums. A Riemann sum for a function f over an interval from a to b is obtained by decomposing the interval first into subintervals. Let delta of xk denote the length of the kth subinterval. From each subinterval, choose a tag point tk, and then form the quantity f at tk times delta of xk. If f at tk is positive, then f at tk times delta of xk is the area of the rectangle based on the kth subinterval with height f at tk. If f at tk is negative, then the quantity f at tk times delta of xk is negative of the corresponding rectangle, the ones which are shown in red here in this picture. Then one takes finer and finer decompositions, so at the limit as the length of the longest subinterval in the decomposition approaches 0, one gets the definite integral from a to b of the function f of x dx. If the function f takes only positive values, then the definite integral from a to b f of x dx is the area of the domain under the graph of the function f and over the x-axis interval from a to b. If the function takes also negative values, then the integral from a to b f of x dx is the difference of those domains where the function takes positive value, the areas of those domains where the function takes positive value, and the area of those domains where it takes negative value. So in the case of this picture, the integral from a to b f of x dx is the difference of the areas of the blue domains and the red domain. Since integrals are limits of Riemann sums, one may approximate integrals numerically by computing certain Riemann sums. To that end, we start by decomposing the interval of integration from a to b into n subintervals where n is some positive integer, and then the length of each subinterval is b minus a divided by n. That is denoted by delta of x. So we decompose the interval from a to b into n subintervals of equal length. The kth subinterval is therefore a plus k minus 1 times delta of x to a plus k times delta of x. A Riemann sum corresponding to this decomposition is of the form summation k from 1 to n f at tk times delta of x, where the tag point tk is on the kth subinterval. So it satisfies a plus k minus 1 times delta of x is at most tk, and that is at most a plus k times delta of x. These points tk can be chosen freely. There are some obvious choices. We may choose tk to be the left endpoint, the right endpoint, or the midpoint of the corresponding subinterval. And these 3 different choices lead to 3 different numerical approximations of integrals. The first one is a left approximation. Then we choose tk to be the left endpoint of the corresponding kth subinterval. Therefore, the left approximation for the integral is summation k from 1 to n, function f evaluated at a plus k minus 1 times delta of x, and that multiplied by delta of x. So that corresponds to the rectangles, the green rectangles shown here in this picture, whose height is given by the value of the function at the left endpoint of each subinterval. Then we may choose the right endpoint instead of the left endpoint. We get the right approximation. It is summation k from 1 to n f at a plus k times delta of x. This Riemann sum corresponds to the choice of tk being the point a plus k times delta of x, and therefore the height of the corresponding rectangle on the kth subinterval is the value of the function at the right endpoint of that subinterval as indicated in this picture. Then we have the midpoint approximation, in which the point tk is the midpoint of the corresponding case subinterval, that is the point A plus k minus 1/2 times delta of x times delta of x. And here this Riemann sum corresponds to the areas of the rectangles whose height is the value of the function at the midpoints of these subintervals. These are the three basic numerical approximations of definite integrals. Problems to be considered are the following. The first one, compute the integral from -2 to 2 of the absolute value of x plus 1 minus the absolute value of x minus 1. We will compute this integral by relating its value to the area of a domain, which area can then easily be computed. In the second problem, the graph of the function is given, and our task is to estimate the value of the integral from -3 to 3 of this function based on this graph. That is, we must estimate the value of the red area in this figure. In the third problem, the speed of a car is given by a table, and we have to estimate the distance traveled. In this problem, our task is to compute the integral from -2 to 2 of the function absolute value of x plus 1 minus absolute value of x minus 1 dx. We solve this problem by drawing the graph of the function and then computing the integral as the area of the domain under the graph. It turns out that this area can easily be computed, and this area is then the value of this integral. And in order to be able to draw the graph of the function, we must first get rid of the absolute value signs. So we will simplify the function in question. Within the absolute value signs, we have the absolute value of x plus 1 minus the absolute value of x minus 1. We start by the innermost absolute values, and we observe that the absolute value of x plus 1 is x plus 1 if x is greater than or equal to -1, and it is negative of x plus 1, that is minus x minus 1, if x is less than -1. Likewise, the absolute value of x minus 1 is x minus 1 if x is greater than or equal to 1, because then x minus 1 is non-negative. If x is less than 1, x minus 1 is negative, and the absolute value of x minus 1 is minus of the quantity x minus 1, that is 1 minus x. Our task is to simplify the function to be integrated, that is, the expression the absolute value of the absolute value of x plus 1 minus the absolute value of x minus 1. We started by simplifying the innermost absolute values. We obtained expressions for the absolute value of x plus 1 and for the absolute value of x minus 1, which expressions are valid on certain intervals for x. The breakpoints were 1 and -1. For absolute value of x plus 1, it is -1. For the absolute value of x minus 1, it is 1. Now we may plug these representations in, and we get that the function to be integrated, the absolute value of x plus 1 minus the absolute value of x minus 1 is the absolute value of the quantity x plus 1 minus, within parentheses, x minus 1. And this if x is greater than or equal to 1. If x is between -1 and 1, we get the expression the absolute value of x plus 1 minus, within parentheses, the expression 1 minus x. And if x is less than -1, we get the absolute value of minus x minus 1 minus 1 minus x. These simplify further clearly, and we get that the absolute value of x plus 1 minus the absolute value of x minus 1 equals 2 if x is greater than or equal to 1. And if x is between -1 and 1, it is 2 times the absolute value of x and it is 2 if x is less than -1. We may still get rid of the last absolute value that we had, and we observe that the expression, the absolute value of x plus 1 minus the absolute value of x minus 1 is 2 if x is greater than or equal to 1. It is 2 times x if x is between 0 and 1. It is negative 2 times x if x is between -1 and 0, and it is 2 if x is less than -1. Therefore, the graph of this function looks like this letter V. This is the graph of the function y equals the absolute value of x plus 1 minus the absolute value of x minus 1. And our task is to compute the integral from -2 to 2 of this function. This means that we have to compute the area of the yellow domain indicated here in this picture. Now this area is easy to compute because it consists of 2 rectangles and 2 triangles. The leftmost rectangle is on the interval from -2 to -1, and its height is 2, therefore its area is the length of the base, which is 1, times the height, which is 2. So the area of the leftmost rectangle is 2. Likewise, the area of the rightmost rectangle is also 2. And the 2 triangles in the middle, they add up to 1 rectangle. So the area that we have is 2 plus 1 plus 1 plus 2, which equals 6. So we conclude that the value of this integral from -2 to 2 of the absolute value of x plus 1 minus the absolute value of x minus 1 dx is 6. That is the area of the yellow domain. The graph of the function f is given in this picture. Our task is to estimate using left Riemann sums with 12 subintervals of equal length the value of the integral from -3 to 3 f of x dx. So what we have to do is we have to estimate the area of this red domain. And we are advised to estimate using left Riemann sums. That is, Riemann sums where the tag points are the left endpoints of the corresponding subintervals, and we are also told that we have to use 12 subintervals of equal length. So we decompose first the interval of integration, that is the interval from -3 to 3, into 12 subintervals of equal length, and the division points are -3, -2.5, and so forth. The length of each subinterval is 6 divided by 12, that is just 1/2. And as tag points, we are told to use the left endpoints. So we form the Riemann sum, and it corresponds to the areas of the rectangles that are now being drawn in this picture, and whose height is the value of the function at the left endpoint of the corresponding subinterval. The total area of these blue and red rectangles is now the Riemann sum, for which we have to compute the value, and that Riemann sum is the required estimate for the integral from 3 to 3 for the function f of x dx. In order to estimate the integral from -3 to 3 of f of x dx by left Riemann sums, we next need to estimate the value of the function f on the left endpoints of these subintervals in question, and that must be done by using this figure. On the negative side, we have 6 subintervals, and the value of the function at the left endpoints of these 6 subintervals can be estimated from this figure. At -3 it is about 1.6, at -2.5 it's about 176, at -2 it is 175, at -1.5 it is 137, at -1 it's 1, at -0.5 it is also 1 approximately, and at 0 it is approximately 1.5. These estimates have been obtained simply by looking at these graphics. Likewise, on the positive side, we have to compute the value of the function at the left endpoints or we have to estimate these values. And from this picture we get that the value at 0.5 is about 2.12, at 1 it's about 268, at 1.5 275, at 2 248, at 2.5 198, and at 3 125. We actually do not need the value of the function at the endpoint 3 because it is the right endpoint of the last subinterval, and therefore in the left approximation does not enter in the computations. So we have these values for the function at the endpoints of the subintervals of this decomposition, and the Riemann sum is now summation k from 1 to 12 f at the tag point tk times delta of x. And the tag points are the left endpoints. And delta of x is 0.5. That can be taken outside as a common factor, and we have that our approximation for the integral from -3 to 3 f of x dx is 0.5 times the sum of the values of the function at the points tk. And this means that the left 12 estimate is 0.5 times the sum of these quantities up to the second to the last. So the last one, that is when tk equals 3, that we do not take anymore in the computation. And this sum is approximately 11. So we conclude that the value of this integral from -3 to 3 f of x dx is approximately 11. And 11 divided by 6 is 1.8. This means that the average value of the function f on the interval from -3 to 3 is about 1.8. And this means that the rectangle whose base is the interval from -3 to 3 and whose height is about 1.8 has the same area as the domain under the graph of this function and over the interval from -3 to 3. The speed of a racing car during the first 10 seconds of a race is given in the table below. Our task is to estimate the distance traveled during that time. Time is measured in seconds from the start of the race, and the speed is measured in meters per second. So at the start of the race, time is 0, speed is 0. After 1 second, speed is 14 meters per second, and so forth. In order to get an idea of what is happening, it is useful to picture this data graphically. We draw these data points in the coordinate plane. Here the x-axis has the unit 1 second, and the y-axis has the unit 10 meters per second. That is speed, and x-axis is time. These data points corresponding to the table given are drawn here in this coordinate plane, and we connect these points simply manually to each other to draw a graph which estimates the speed of the car at any given time. And our task is to estimate the distance that this car has traveled. So during the first second, at the start of the first second, the speed is 0. In the end of the first second, the speed is 40 meters per second, and then so forth. So time interval is 1 second. So delta of t is 1. And next we compute the average velocity during the time interval. So that is for the first time interval, that from 0 to 1 seconds, the average velocity is the average of 0 and 14, so it is 7. And during the second time interval, the average is the average of 14 and 28, it's 21, and so forth. So these numbers that we have for the average velocities, they are the averages of 2 subsequent numbers in the first table. So they are average velocities during the corresponding time intervals. Our task is to estimate the distance traveled by these race cars during the 10 first seconds of the race. And we had computed the average speeds during the first, second, third, fourth, and so forth second of the race. The acceleration is quite amazing. So during the first second, the average speed is 7 meters per second, and during the next second, the average speed is already 21 meters per second, and so forth. In order to estimate the distance traveled, we compute the distance traveled during time intervals. So during the first time interval, the car travels 7 meters per second times 1 second. That is just 7 meters. During the second time interval from 1 second to 2 seconds, the car travels 1 times 21 meters per second. So 1 second times 21 meters per second, that is 21 meters, and so forth. So the numbers in meters of the distance traveled are precisely the same as the average speeds or velocities during the different time intervals, because the speed is given in terms of meters per second and the length of each time interval is just 1 second. So we conclude that during the first second the car travels 7 meters, during the next second it travels 21 meters, during the third second it travels 35 meters, and so forth. So here we have the speed graph, and the distance traveled is just speed times time. And we use, on various time intervals, we use the average speeds. So during the first second we get 7 meters and so forth, and this speed times time is also the area of the corresponding rectangles during various time intervals. So we conclude that the total area of the rectangle shown here is the distance traveled during that time. So our task was to estimate the distance traveled, and we computed this table. During the first time interval 7 meters, during the second 21 meters, and so forth. So from this table it is easy to simply add up the last numbers of the last row, and we conclude that the distance traveled during 10 seconds is 403 meters approximately. And this means that the average speed during the first 10 seconds is 40.3 meters per second, and that is approximately 90 miles per hour. These cars are blazingly fast. The considerations that we use to estimate the distance traveled tell us that if s of t is the speed of an object at time t, then the distance traveled during a time interval is simply the same as the area of the domain under the graph of the speed function and over that particular time interval. This means that this is integral from a to b s of t dt. Speed may be measured, for example, in meters per second. And if time is also measured in seconds, then the unit of this integral from a to b s of t dt is meters. The speed data corresponds to that of a Formula 1 car in this example. They are incredibly fast. A typical acceleration of a Formula 1 car from 0 to 200 kilometers an hour, that is from 0 to 124 miles per hour, is about 3.8 seconds. The braking is even more incredible. The braking deceleration is up to 5 or 6 G. That means 48 to 58 meters per second squared. So they accelerate incredibly fast and brake even faster.